Hi, in this video I'm going to talk about big O notation. So, why do we need big O notation? In order to compare efficiency of algorithms that achieve the same purpose, such as sorting algorithms, like bubble sort, merge sort, bucket sort, in order to be able to compare these algorithms' runtime and at what time we need to use which algorithm, in order to decide these things, we need to have some kind of metric to label the runtime of these algorithms to say one algorithm is better than the other. For example, there is a reason why we don't use bubble sort because we know its even best case running time is O(n) squared. On the other hand, merge sort's worst case running time is O(n) log n. Looking at these two sorting algorithms' big O notation value tells us which one is more efficient. Apparently, in this case, merge sort because n log n is a slower growing function than n squared. Big O notation can be used to describe best, average, and worst case running times of an algorithm. What is big O notation? It provides upper bound on the running time of an algorithm, which means it tells us that no matter what the input is, an algorithm at worst will do big O of certain function. For example, when we say merge sort's worst case running time is O(n) log n, we mean that n log n will be the worst it will perform. So in order to understand the big O notation and how it provides us a framework where we can label functions with their runtime, we need to understand the growth of functions first. So we describe running time as a function of input size. Different functions have different growth rates. For example, if n is our function's input, so n is a number. So log n as a function is a slower growing function than n. And n is a slower growing function than n log n, then n squared 2 to the n power and n factorial. It goes, so from left to right, all the functions are growing. In terms of their growth rate, they are increasing. So ideally, you will want your algorithm to be more to the left, the running time of your algorithm, rather than more towards the right, which will mean your algorithm is not as efficient. So the smaller the growth rate of a function that represents an algorithm, the more efficient it is. So here I put together a function which doesn't really do much, but just to show how we are calculating according to the input size the running time of an algorithm. This function foo, getting a number n, which is a number, an integer, let's say, it has 3 loops over here, and it constant logs. Let's say constant log is 1 unit, and in this case, how many times we're gonna run the constant log? Each loop is looping n times, which means n times n times n, which gets us to n cubed. Plus, because after this operation is done, then the next one takes place. That's why we are adding it. So as we see it here, n cubed, and then over here, we have a numbers array, which is empty right now, but again, we have another loop that loops over all the n numbers. I mean, n times it's looping over the loop, and then it gets the date and gets the milliseconds and pushes to the numbers array. So since this is the now, getting the date and plus pushing it, these are constant operations. The constant operations in O notation, they have no effect in the end result. So we consider these two, even though there are 2 operations here, we consider them as O1, which has no effect. So in here, we are doing this O1 operation n times. Because it's now dependent on the input size, we say it's running n times. And lastly, I'm calling sort on the numbers array. So if you think that numbers sort let's say we are using merge sort here. Let's say JavaScript is using merge sort, one of the efficient sorting algorithms. It's n log n. So over here, we already know n log n is our running time. And so our last formula becomes, for this algorithm, n cube plus n log n steps to execute to completion. So what Oh Notation says here is, out of all these functions, we can get rid of the constants. In our case, there are no constants, but there could be. So constants don't matter. And out of every other function that we have on the left and right side of the plus sign, what matters is the function that grows the fastest. The reason being, once we get to a large enough n, the growth rate of, in this case, n cube, will dominate every other function's growth rate. And it will determine how much the algorithm will take. So because of this, this algorithm's running time is set to be O(n cube). Again, the reason is that when we get to a certain n value, the result of above equation will be dominated by the highest growing function, which is n cube in above case. This will make other terms in formula insignificant. Big O notation allows us to specify the leading factor in given algorithm's running time. So big O notation in this case tells us one thing. This algorithm's upper bound is dominated by n cube. So it will do, as in the worst or best case, depending on which analysis you're making, it will be determined by the n cube in this case. In our case, it's the worst, best, average case, because since this loop will always run, we don't have any other case but always n cube in this part. So best case, average, and worst case will be n cube. So that is it for this video. Thanks for watching.